Let's look at an example of area estimation using left and right sums. Estimate the area under the graph of f of x equals x cubed plus 1 from x equals 1 to x equals 3. Use 4 rectangles and get estimates using both left endpoints, that would be L4, and right endpoints, that would be R4. So to do this, we're going to start by drawing a graph of the function. And we're going to determine the width of each rectangle that we're going to use. And we're going to draw in the rectangles. So this is a good way to get a visual picture of what's going on here so you can actually understand the math. And then if you need to, you can draw separate graphs for both the left and the right endpoints. Okay, so let's start by drawing a graph of this. So this is an x cubed plus 1, and you can do this on a calculator or if you need to plot points by hand. We know it's a cubic. So for this case, it's x cubed plus 1. It's going to look something like this. It looks like the x cubed graph that has been shifted up by 1 unit. And the area that we're looking at is from 1, which is right here, up to 3, which is right here. So it's going to go all the way up here, all the way to the graph. And so we're talking about this area all in here. And so if we notice, this function is increasing throughout this interval 1 to 3. And so we're going to try and find this area by using 4 rectangles. Okay, so let's start by looking at left endpoints. So here's the graph, and I've drawn in the 4 rectangles that we're going to use for the left endpoints. And we know the width of each rectangle has to end up being a half. So that is my delta x. So if you remember, n was the number of rectangles, n in this case was 4. And my delta x is the width of each rectangle, which you can actually calculate if you think we're doing 3 minus 1 is the length of the interval from 3 to 1. So the distance we could get from 3 minus 1, and we want to divide that into 4 rectangles. And so 3 minus 1 is 2, 2 over 4, that ends up being half. Okay, and so we want to calculate L4. This is left endpoints with 4 rectangles. And so to do that, we're going to get a half, which is the width, times, in this case, the value of the function at 1, because we're looking at left endpoints, plus a half times the value of the function at, in this case, 1.5. And then the next one will be a half times the value of the function at 2. That's right here. That's this rectangle right here, the area of this one, the third one. And then the last one, a half times the value of the function at 2.5. And if we do this, that should give us our area estimation using left endpoints. So I can factor out the half. There's a half that's constant throughout here because it's always going to have a width of a half each rectangle. And the values of the function I can get by just plugging into a calculator or plugging into the formula. I have the formula of the function x cubed plus 1. So for instance, f of 1, that would end up being 1 cubed plus 1. So I'll write that in here. And then the next one would be f of 1.5, that would be 1.5 cubed plus 1. And then the next one is f of 2. F of 2 would end up being 2 cubed plus 1. And then the last one is 2.5, so that would be 2.5 cubed plus 1. And then close my parentheses here, my bracket. Okay, so now I have a half times each of these values, and if I do all of this out on a calculator here, I end up getting 16. And if we look at the graph here, we see that this estimate of 16, this has to be an underestimate because there are these little bits right in here that we're not getting that we should have gotten for the area. So when we get this value of 16, it's actually going to be an underestimate. Okay, now let's look at right endpoints. So here's the graph, and now I have the rectangles drawn in for right endpoints. And in this case, I still have 4 rectangles, so my n is still 4, and my delta x is still going to be a half. That didn't change. And now I'm going to look at R4. So R4 would be using right endpoints with 4 rectangles. And so the width is going to be a half for all of them. So I'm just going to factor out that 1/2. And then I'm going to get the value of the function at, and the first one is going to be at 1.5. That's what the height of this first rectangle would be. So that's f at 1.5, plus the next one is going to be f at 2. And then the next one is going to be f at 2.5. That's right here. And then my last one is going to be f at 3. So that's this last big rectangle right here. Notice as a height determined by f of 3. All right, so I still have my 1/2 out front. And now I can plug into the formula here, x cubed plus 1. So this first one will be 1.5 cubed plus 1. And the next one will be 2 cubed plus 1. And then the next one is 2.5 cubed plus 1. And then the last one is 3 cubed plus 1. And close my bracket. And if you do all this out on the calculator, you end up getting 29. And we see that this 29 now is an overestimate. I have all of this here that shouldn't be there. This is not part of the area under the curve. So when I got this 29, this ended up being an overestimate. Okay, so here is the graph, and let's compare with the actual area. So I had the function f of x equals x cubed plus 1, and we were looking from 1 to 3. And we found that the area was somewhere between 16 and 29. We had our lower estimate and our upper estimate. And the actual area is 22. So that does indeed fit within the range of 16 to 29. And of course, if we wanted to get a better estimate, to get a smaller range, we would use more rectangles.